Hey everyone, and welcome. Today we're opening up the Architect's Toolkit. We're going to explore the amazing math tools, the kind of stuff you'd see in advanced courses like Unit 2, that are used to design and build literally everything around us, from a simple, elegant curve to the most massive, mind-blowing structures you can imagine.
So think about this for a second. How is it even possible that the same math can describe the steepness of one tiny piece of a curve and also the entire volume of a giant dome? It seems kind of wild, right? Well, that's the core question we're tackling today. Turns out, the secret is in one single, beautifully interconnected set of tools. So let's dive in and check them out.
Okay, first step in our toolkit is differential calculus. Now I want you to think of this as the blueprint phase of any big project. This is where we zoom way in on the tiniest details, figuring out every little change with perfect precision, from one single point to the very next.
Yeah, the key here is to see this not as abstract numbers, but as a powerful magnifying glass. An architect uses it to find the exact slope of a wheelchair ramp, or the precise angle of a futuristic roof, or even where the most stress is on a support beam. It's all about understanding what's happening at one single frozen moment in time.
Now, a really cool tool for this is something called the Leibniz theorem. Imagine you're designing a building where, say, the width is changing at the same time its height is changing. You've got two things happening at once. This theorem gives you a step-by-step way to figure out their combined effect without your brain exploding from the complexity. It's a specialized tool for a surprisingly common design problem.
And this just shows you how many different gadgets are in the blueprinting kit. You can find the highest and lowest points of a structure, that's maxima and minima. You can measure the sharpness of a curve, which is absolutely essential for those flowing liquid-like buildings. You can even use something called envelopes to figure out the absolute boundary a moving part of a design, like a retractable roof, will ever reach. Each one is a specific tool for getting the design just right.
Okay, so our blueprints are perfect. Now what? We have to actually build the thing, right? Once all those tiny details are locked in, we need to construct the object. And that is where our second major tool, integral calculus, comes into play. This is the math of adding things up, of building something whole from all the little pieces.
Really, these two types of calculus are just two sides of the same coin. It's pretty elegant. If differential calculus tells us everything we need to know about a single brick, integral calculus tells us how to add up millions of those bricks to get the volume of the entire wall. It's how we scale our design up from a single point to the whole amazing structure.
And check out the kind of heavy lifting it can do. Using double and triple integrals, we can calculate the exact square footage of a weirdly shaped floor plan, or the total volume of air inside a concert hall. We can even figure out the surface area of complex shapes, like exactly how much glass you'd need to cover a geodesic dome. This is all about building real, measurable things.
Now, sometimes the construction job is just really tough. That's when you have to bring out the heavy machinery. In our toolkit, that's the beta and gamma functions. Seriously, think of these as specialized power tools. They're designed to solve very specific, very difficult problems that pop up when your designs start getting into advanced physics or statistics.
So we have tools to design the details and tools to build the structure. But what language are we even using to describe these shapes in the first place? That brings us to the final piece of our toolkit, analytical geometry. This is the fundamental grammar of form.
A good architect really has to be bilingual. You've got the Cartesian system, your classic X and Y grid, which is perfect for describing things like rooms, walls, and city blocks. But if you want to design a spiral staircase, or a big circular window, or a domed roof, the polar system, which uses an angle and a distance, is just way more natural, way more efficient. You got to speak the right language for the shape you're trying to make.
And this language has its own deep, fascinating grammar. A concept like pole and polar, for instance, describes this really precise fundamental relationship inside shapes like ellipses. It's a core rule that connects a single point to an entire line, which just goes to show you how structured and powerful the language of geometry really is.
So, there we have it. We've got our blueprints, we have our construction process, and we have the language to describe it all. Now let's put the whole toolkit together and see what we've got.
And this right here is the big takeaway. These three fields aren't just separate subjects you memorize for a class. No way. They are essential, integrated parts of one complete system.
You need the language of geometry to describe a shape. You need the blueprints from differential calculus to perfect its details. And you need the construction tools of integral calculus to actually build it. And with all three, you can model pretty much anything in the world.
So I'll leave you with this question. Now that you have this toolkit, this language, these blueprints, these construction tools, what will you build? What complex system out there in the world can you now look at and see in a totally new way? The possibilities, as you can probably guess, are endless.